There is a small, fragile spacecraft, no bigger than a car, that has been sailing through the cosmos for nearly 50 years. It is now more than 15 billion miles away from Earth, a distance so vast that a radio signal, travelling at the speed of light, takes over 21 hours to reach it. This is Voyager 1, the most distant human-made object that has ever existed, and it is still talking to us, whispering back data from the dark space between the stars. When people hear this fact, their minds often leap to a simple, almost innocent question. If 2 Voyagers were so successful, why did we never build a third? Why is there no Voyager 3? It seems like a logical next step, a straightforward continuation of a legendary program. But the answer to that question is not about a lack of ambition or a simple shortage of money. It is a story that unravels the very nature of how we explore the unknown, revealing a truth far more fascinating than the myth of a missing spacecraft. To understand why there is no Voyager 3, you first have to appreciate the sheer impossibility of the original mission. The Voyagers were not built for a leisurely trip through the solar system. They were engineered for a once-in-a-lifetime cosmic alignment, a planetary parade that occurs only once every 176 years. This alignment allowed a single spacecraft to use the gravity of one giant planet to slingshot itself to the next, a technique that saved fuel, time, and money. The entire mission was a masterclass in astronomical timing, a perfect window that opened in the late 1970s and then slammed shut for nearly 2 centuries. To build a Voyager 3 after that window closed would be like trying to catch a train that had already left the station. You could build the most beautiful train car in the world, but without the tracks, without the alignment, it would go nowhere useful. And yet, the real reason we never sent a third Voyager goes even deeper than a missed planetary alignment. It has to do with the way our priorities shift, the way a nation's focus can drift from the outer planets to the inner ones, from the grand tour to the practical business of building a space shuttle and studying our own planet. If you are the kind of person who wonders about these hidden truths, who looks at the night sky and asks why, then you are exactly the kind of explorer this channel is for. Before we go any further, take a moment to like this video and subscribe to This Is Space. By joining this community, you are helping us uncover the stories behind the missions, the ones that textbooks often leave out. Because the question of Voyager 3 is not a simple oversight in history. It is a mirror that reflects our own changing dreams, our own limited resources, and the cold, hard reality of what it truly means to reach for the stars. What happened next would redefine our understanding of the solar system, and it began with a decision that was made not when the Voyagers were launched, but long before any of them ever left the launch pad. The story of why there is no Voyager 3 begins not with a failure of imagination, but with a rare and extraordinary gift from the universe itself. In the early 1960s, a NASA engineer named Gary Flandro was studying the outer planets when he made a startling discovery. He realized that the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, were about to align in a configuration that would not occur again for 176 years. This alignment meant that a single spacecraft, launched at just the right moment, could use the gravity of each planet to slingshot itself to the next, like a stone skipping across a cosmic pond. It was a gravitational highway, a free ride to the outer solar system that nature provided only once every 2 human lifetimes. The window for this grand tour would open in the mid-1970s and close just a few years later. If NASA missed it, they would have to wait until the 22nd century for another chance. The mathematics of this alignment were breathtaking in their precision. To take full advantage of the opportunity, a spacecraft would need to reach Jupiter by the early 1980s, then use that planet's immense gravity to swing towards Saturn, then onward to Uranus, and finally to Neptune. The entire journey would take about 12 years, a fraction of what a direct flight to any one of these worlds would require. But there was a catch. The alignment was so specific that the launch window was incredibly narrow. If you missed the launch by even a few weeks, the entire trajectory would fall apart, and you would be left with a spacecraft that could only visit 1 or 2 planets before drifting aimlessly into the void. This is why the Voyager program was designed with such urgency and such precision. It was not a leisurely exploration. It was a race against time. The original plan called for 2 spacecraft, Voyager 1 and Voyager 2, each designed to follow slightly different paths. Voyager 1 would take a faster, more direct route to Jupiter and Saturn, allowing it to conduct close flybys of those planets and their moons. Voyager 2 would take a slower, more cautious trajectory, exploring Jupiter and Saturn as well, but with the option to continue on to Uranus and Neptune if the mission went well. This dual approach was a masterpiece of engineering and risk management. If Voyager 1 failed, Voyager 2 could still gather crucial data, and if both succeeded, humanity would gain an unprecedented view of the outer solar system. But here is the key point that most people miss. The Voyagers were not built to explore interstellar space. They were built for a 4-year primary mission to Jupiter and Saturn. Everything after that was a bonus, a gift that kept on giving. The alignment itself was a thing of mathematical beauty, but it also imposed severe constraints on the spacecraft design. Because the Voyagers had to be lightweight and durable enough to survive the extreme cold and radiation of deep space, engineers at NASA's Jet Propulsion Laboratory made a series of trade-offs that would define the mission forever. They chose nuclear power in the form of radioisotope thermoelectric generators because solar panels would be useless so far from the sun. They built the spacecraft out of aluminum and titanium, with a protective coating to shield them from cosmic radiation. They installed a suite of scientific instruments including cameras, spectrometers and magnetometers, all designed to capture the first close-up images of worlds that had only ever been blurry dots in the sky. And they included a special payload that would become the most famous message in a bottle ever launched: the Golden Record. The Golden Record was the brainchild of astronomer Carl Sagan and his team. It was a copper phonograph record, plated with gold, containing sounds and images of Earth. There were greetings in 55 languages, the sounds of wind and rain and whales, and 116 images depicting life on our planet. The intention was to communicate with any intelligent civilization that might one day find the spacecraft. It was a gesture of hope, a time capsule of humanity's existence. But the record also served a deeper purpose. It reminded everyone involved in the project that the Voyagers were not just machines. They were ambassadors carrying the story of our species into a universe that had never known we existed. As the launch date approached, the tension at Cape Canaveral was palpable. The first Voyager, Voyager 2, lifted off on August 20th, 1977, aboard a Titan IIIE rocket. Voyager 1 followed on September 5th, aboard the same type of rocket. The launches were nearly flawless, a testament to the skill of the engineers and technicians who had spent years preparing for this moment. But the real challenge was yet to come. The spacecraft had to survive the brutal radiation belts of Jupiter, the icy rings of Saturn, and the long, dark stretches of empty space between the planets. And they had to do it all with computers that had less processing power than a modern calculator. The journey to Jupiter took about 2 years. When Voyager 1 reached the giant planet in March of 1979, it sent back images that left scientists speechless. The Great Red Spot, a storm larger than Earth, churned with a violence that defied description. The volcanic moon, Io, was spewing sulphurous plumes into space, and the icy moon Europa showed signs of a cracked surface that hinted at a hidden ocean beneath. These discoveries were just the beginning. At Saturn, Voyager 1 revealed the intricate structure of the rings, with thousands of tiny ringlets and shepherd moons that kept them in place. It also found that Titan, Saturn's largest moon, had a thick atmosphere rich in nitrogen, a world that resembled a frozen version of early Earth. But the true marvel of the Grand Tour was yet to come. After Voyager 1 completed its flybys of Jupiter and Saturn, it was sent off on a trajectory that would take it out of the plane of the solar system, heading toward interstellar space. Voyager 2, however, took a different path. It used Saturn's gravity to slingshot itself toward Uranus, a planet that had never been visited by any spacecraft. In January of 1986, Voyager 2 flew past Uranus, revealing a world tipped on its side, with a magnetic field that was wildly misaligned, and a set of dark rings that had never been seen before. The spacecraft then hurtled toward Neptune, arriving in August of 1989. There it captured images of the Great Dark Spot, a storm system as large as Earth, and the Moon Triton, which had geysers of nitrogen ice erupting from its surface. The Grand Tour was complete. In just 12 spacecraft had visited 4 giant planets, discovered dozens of moons, and transformed our understanding of the solar system. It was an achievement that had never been attempted before and will likely never be attempted again. The alignment that made it possible will not return until the year 2249, and by then humanity will have changed beyond recognition. But the Voyagers themselves are still out there, still travelling, still sending back data from a place no human-made object has ever gone before. The question of why we never built a Voyager 3 then is not really a question about a missing spacecraft. It is a question about the limits of opportunity, the fleeting nature of cosmic alignments, and the quiet realization that sometimes the universe gives you a gift that can never be repeated. And once you understand that, you understand that the Voyagers were not just a mission. They were a moment in time, captured forever in the cold, silent void. The 2 Voyagers were never meant to be alone. When they launched in 1977, they were part of a small fleet of spacecraft designed to exploit a rare opportunity in the solar system. But what they achieved, and what they continue to achieve, has made the idea of a third Voyager almost irrelevant. Because the truth is that Voyager 1 and Voyager 2 have already done what no single spacecraft could ever do. They have mapped the outer planets, revealed worlds beyond imagination, and then kept going, pushing into the unknown that lies beyond the Sun's influence. Let us begin with the giants. Voyager 1 reached Jupiter in March of 1979, and the images it sent back were a revelation. The Great Red Spot, a storm that had been observed for centuries, was seen in unprecedented detail. It was larger than Earth, and it was not alone. Voyager 1 discovered that Jupiter's atmosphere was a chaotic tapestry of bands, swirls, and storms, all driven by the planet's rapid rotation and internal heat. Then it turned its cameras toward the moons. Io was a shock. Instead of a cratered, dead world, it was covered in volcanoes, actively erupting with plumes of sulfur that rose hundreds of miles into space. It was the most volcanically active body in the solar system, and no one had expected it. Europa, meanwhile, showed a surface of cracked ice, suggesting an ocean beneath. That ocean, we now believe, may be one of the best places in the solar system to search for life. Voyager 2 arrived at Jupiter 4 months later, in July of 1979, and it confirmed everything its twin had seen while adding its own data. Together, the 2 spacecraft revealed Jupiter as a dynamic, living world, not just a static ball of gas. They also measured its magnetic field, its radiation belts, and the faint ring system that encircles the planet. In just a few months, they changed the way we think about the largest planet in the solar system. Then came Saturn. Voyager 1 made its closest approach in November of 1980, and the images of the rings were breathtaking. The rings were not solid bands but thousands of individual ringlets, each composed of ice and rock particles. Gaps in the rings were carved by the gravitational influence of small moons, like shepherds herding sheep. The moon Titan was the main target. It had a thick atmosphere, denser than Earth's, and it was shrouded in a haze of organic molecules. Voyager 1 could not see the surface, but it measured the atmosphere and found it rich in nitrogen and methane. It was a world that looked remarkably like an early Earth, frozen in time. After Saturn, Voyager 1's trajectory was set. It was aimed upward, out of the plane of the solar system, to study the direction of the Sun's magnetic field. That decision meant it would not visit Uranus or Neptune. That task fell to Voyager 2. Voyager 2 reached Saturn in August of 1981, and it added even more detail. It discovered new moons, studied the rings in different wavelengths, and measured the planet's magnetic field. Then it was on to Uranus, a journey that took 5 years. When Voyager 2 arrived in January of 1986, it was the first and only spacecraft to visit the 7th planet. Uranus was a pale blue world, almost featureless at first glance. But closer inspection revealed a strange magnetic field, tilted at an extreme angle relative to the planet's rotation. The rings were dark and narrow, unlike the bright rings of Saturn, and the moons were a collection of icy worlds, each with its own unique surface. Miranda, the smallest of the major moons, was a jumble of terrains, with cliffs and valleys that suggested a violent past. After Uranus, Voyager 2 had one more target. Neptune, the last of the gas giants, was a faint blue dot in the distance. The spacecraft arrived in August of 1989. Neptune was a surprise. It had a great dark spot, a storm system as large as Earth, and winds that reached speeds of over 1,200 miles per hour, the fastest in the solar system. The moon Triton was even more astonishing. It had geysers of nitrogen ice erupting from its surface, a sign of active geology on a world that should have been frozen solid. Voyager 2 had completed the Grand Tour, visiting all 4 gas giants in a single mission. No other spacecraft has ever done that, but the Voyagers were not done. After their planetary encounters, they continued outward, their trajectories carrying them into the farthest reaches of the solar system. In 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's influence gives way to interstellar space. It became the first human-made object to leave the solar system. Voyager 2 followed in 2018, crossing the boundary at a different location. Now both spacecraft are in interstellar space, sending back data about the environment beyond our Sun's protective bubble. They measure cosmic rays, magnetic fields, and plasma waves. They are still teaching us, decades after they were launched. The spacecraft themselves are remarkable. They are powered by radioisotope thermoelectric generators, which convert heat from the decay of plutonium into electricity. And by around 2030, they will no longer be able to operate any of their instruments. But until then, they keep going. They are now over 15 billion miles from Earth, moving at speeds of about 38,000 miles per hour. It takes more than 22 hours for a signal from Voyager 1 to reach Earth. The spacecraft are so far away that their signals are incredibly faint, barely detectable by the Deep Space Network. The golden records are still aboard, containing sounds and images of Earth. They are time capsules, meant to be discovered by some future intelligence, or perhaps by no one at all. The irony is that the Voyagers are more likely to be found by humans of the far future, if they ever develop the technology to catch up to them, than by any alien civilization. But that is part of the beauty of the mission. It is an act of faith, a message in a bottle, thrown into the cosmic ocean, and yet the question lingers. Why did we stop? Why did we not build a Voyager 3, 4, 5 and send them out into the galaxy? The answer lies not in a lack of ambition, but in a shift in priorities. After the Voyagers, NASA turned its attention inward. The Space Shuttle program consumed resources and attention. The focus shifted to Mars, with orbiters and rovers designed to search for signs of past life. The Hubble Space Telescope was launched, opening a new window on the universe. The outer planets were not forgotten, but they were no longer the priority. The next mission to the outer solar system, Galileo, did not reach Jupiter until 1995, and it was a very different kind of mission. It was designed to orbit Jupiter, not fly past it, and it studied the planet and its moons in detail. But it was not a Voyager. It did not have the same scope, the same ambition. The truth is that the Voyagers were a product of a unique moment in history. They were conceived during the space race, when budgets were large, and ambition was even larger. They were designed to exploit a rare planetary alignment that would not come again for 176 years, and they succeeded beyond anyone's imagination. But the era that produced them is over. The political will, the public support, the funding, all of it has shifted. The Voyagers are still out there, still sending back data, still teaching us. They are a reminder of what we can achieve when we dare to reach for the stars. And they are a challenge to future generations to ask whether we will ever again attempt something so bold. But here is the quiet truth that often goes unnoticed. The Voyagers are not just relics of a bygone era. They are still active, still operational, still pushing the boundaries of human knowledge. Every day they send back data that helps us understand the shape of the heliosphere, the nature of interstellar space, and the conditions that exist beyond the sun's protective bubble. They are the longest-running space mission in history, and they have outlasted every expectation. They were designed to last 4 years. They have lasted over 45, and they will continue until their power runs out, sometime around the year 2030. After that, they will become silent ambassadors, drifting through the galaxy, carrying the story of humanity into the void. And it is that story, the story of what we have achieved and what we have left behind, that leads us directly into the next chapter of this journey. And yet, for all the marvels the Voyagers have achieved, a persistent question lingers in the minds of space enthusiasts and casual observers alike. Why did we never build a Voyager 3? It seems like such a natural next step. After the success of Voyager 1 and 2, why not launch a third, perhaps on a different trajectory, or with upgraded instruments, to continue the exploration of the outer solar system and beyond? The question is asked so often that it has become a kind of myth. A story we tell ourselves about missed opportunities and bureaucratic failure. But the reality is far more revealing, and it cuts to the very heart of how space exploration actually works. The first hidden assumption behind the question is that a Voyager 3 was ever part of the original plan. It was not. The Voyager program was specifically designed to take advantage of the Grand Tour alignment, a planetary lineup that occurs only once every 176 years. That alignment dictated the trajectories, the launch windows, and the spacecraft design. There was no room for a third spacecraft because the alignment itself only required 2. One to handle Jupiter and Saturn, and another to continue on to Uranus and Neptune. Building a third Voyager would have been redundant, a waste of resources that could have been better spent on the 2 that were already built. And so, from the very beginning, the idea of a Voyager 3 was never on the table. But even if it had been, could we have built one? The answer is more complicated than a simple yes or no. The Voyager spacecraft were engineered for a specific mission, with specific power requirements, communication systems, and scientific instruments. Replicating that design today would be prohibitively expensive, not because the technology is outdated, but because the infrastructure that built them no longer exists. The factories that produce the parts have been retooled. The engineers who designed them have retired or passed away. The supply chains have been dismantled. To build a Voyager 3 from scratch, we would have to reinvent the wheel, and the cost would be astronomical. According to modern estimates, a single Voyager-class mission would cost well over $1 billion, and that is before accounting for inflation and the decades of operational support required. In an era of tight budgets and competing priorities, that kind of investment is difficult to justify. And yet, the myth persists. Part of the reason is that the Voyagers have become cultural icons, symbols of human achievement and curiosity. They are the most distant human-made objects, the longest-running space missions, the ambassadors of Earth to the cosmos. It is easy to imagine that we should have sent more of them, that we missed an opportunity to expand our reach. But this overlooks a crucial point. The Voyagers were not designed to be a fleet. They were designed to be a single audacious shot at exploring the outer planets. They succeeded beyond anyone's wildest dreams, and in doing so, they changed our understanding of the solar system forever. Another hidden assumption is that a Voyager 3 would be valuable today, but what would it actually accomplish? The Voyagers have already visited Jupiter, Saturn, Uranus, and Neptune. They have sent back stunning images of the gas giants, their rings, and their moons. They have discovered active volcanoes on Io, geysers on Triton, and a subsurface ocean on Europa. They have measured the magnetic fields, the radiation belts, and the atmospheres of these distant worlds. What more could a third Voyager tell us that the first two have not? The answer is, not much, at least not in the same way. The outer planets are still there, still waiting to be explored, but the low-hanging fruit has already been harvested. The next steps require more advanced instruments, more targeted missions, and a deeper understanding of the questions we want to ask. And that is precisely what has happened. Instead of building a Voyager 3, NASA and other space agencies have pursued a series of follow-up missions that are far more capable than anything the Voyagers could have achieved. The Galileo mission, launched in 1989, spent 8 years orbiting Jupiter, studying its atmosphere, its moons, and its magnetic environment in unprecedented detail. Launched in 1997, did the same for Saturn, spending 13 years in orbit and sending back data that transformed our understanding of the ringed planet and its moons. The New Horizons mission, launched in 2006, flew past Pluto in 2015, revealing a world far more complex and beautiful than anyone had imagined. These missions are the true successors to the Voyagers, not because they carry the same name, but because they carry the same spirit of exploration and discovery. But here is the deeper truth that the myth of Voyager 3 obscures. We have already sent something like a Voyager 3, just under a different name. The Voyager program was never about the spacecraft themselves. It was about the trajectory, the timing, and the opportunity. When the Grand Tour alignment passed, the window for a similar mission closed. But the desire to explore the outer solar system did not disappear. It simply took new forms. The New Horizons probe, for example, was built to explore Pluto and the Kuiper Belt, regions that the Voyagers never reached. It uses modern technology, including faster computers, better cameras, and more efficient power systems. It is, in many ways, a Voyager for the 21st century. And yet, it is not called Voyager 3, because the Voyager name carries a specific legacy that cannot be replicated. The myth of Voyager 3 also ignores the practical realities of deep space exploration. The Voyagers were launched during a brief window of opportunity, but they have been travelling for over 45 years. Their nuclear batteries are slowly dying, their instruments are failing, and their signals are growing weaker. By the time a Voyager 3 could have been built and launched, the original Voyagers would already be decades into their journey. The new spacecraft would have to catch up, which is impossible without a significant technological advantage. And even if it could catch up, what would it find? The Voyagers have already mapped the heliosphere, measured the interstellar medium, and provided the first direct evidence of the conditions beyond the Sun's influence. A third Voyager would be redundant, a duplicate of a mission that has already been accomplished. And yet, there is a nagging sense of loss, a feeling that we have left something undone. The Voyagers are the only spacecraft we have ever sent into interstellar space. They are the only human-made objects to have crossed that boundary, and they will continue to drift through the galaxy for billions of years, long after Earth has ceased to exist. The idea that we could have sent more, that we could have done more, is a testament to our ambition and our curiosity. But it is also a reminder of the constraints we face. Space exploration is not a game of infinite possibilities. It is a discipline of hard choices, limited resources, and unforgiving physics. So the next time you hear someone ask why we never built a Voyager 3, remember the hidden assumptions behind that question. Remember that the Voyagers were never meant to be a fleet. Remember that the Grand Tour alignment was a once-in-a-lifetime opportunity. Remember that we have already sent successors under different names with different goals. And remember that the Voyagers themselves are still out there, still teaching us, still pushing the boundaries of what is possible. The myth of Voyager 3 is a story we tell ourselves about what could have been. But the true story, the one that matters, is about what we have achieved, and that story is far more remarkable than any myth. And yet, the question still lingers in the public mind. If the Voyagers were so successful, if they revealed so much, if they continue to send back data from the very edge of the solar system, why did we stop? Why did we not build a third, a fourth, a fleet of interstellar ambassadors? The answer lies not in a lack of ambition, but in a fundamental shift in priorities, a reorientation of NASA's goals that began even before the Voyagers had completed their primary missions. To understand why there is no Voyager 3, we must leave the spacecraft behind for a moment and look back at Earth, at the political and economic forces that shaped the decades following those twin launches. The Voyager program was a product of a very specific era. The 1970s were a time of relative abundance for NASA, born from the space race with the Soviet Union. The Apollo program had landed humans on the moon, and the agency enjoyed a budget that, at its peak, consumed nearly 4.5% of the entire federal budget. But by the time Voyager 1 and 2 were hurtling toward Jupiter, that era was already ending. The public's fascination with space had waned. The Vietnam War had drained the national treasury, and a growing sense of fiscal conservatism was taking hold. The era of grand, expensive multi-planet missions was drawing to a close. In the wake of the Voyagers, NASA made a deliberate choice. The agency decided to pivot from the outer planets and focus on a new, more visible, and more politically sustainable goal: the space shuttle. The shuttle was meant to be the workhorse of American spaceflight, a reusable spacecraft that would dramatically reduce the cost of reaching orbit. It was sold to Congress and the public as a practical, almost mundane, tool for exploration, a space truck that could carry satellites, conduct experiments, and eventually build a space station. The vision was compelling, but it came at a tremendous cost. The Space Shuttle program consumed the lion's share of NASA's budget for over 3 decades leaving relatively little for ambitious robotic missions to the outer solar system. The shuttle was a national priority, and everything else, including a follow-up to the Voyagers, had to wait. This shift in focus had profound consequences. After the Voyagers, there was a gap of nearly 2 decades before another American spacecraft visited the outer planets. The Galileo mission, which finally reached Jupiter in 1995, was launched from the Space Shuttle in 1989. It was a remarkable mission, but it was also a study in compromise. Galileo's high-gain antenna, a crucial piece of equipment, failed to deploy, forcing the mission to rely on a much slower, smaller antenna. The spacecraft had to be reprogrammed on the fly, its data transmission compressed and rationed. It was a testament to the ingenuity of NASA's engineers, but it was also a stark reminder of the challenges that came with the new, more constrained era. Galileo was not a Voyager 3. It was a different kind of mission designed for a different time, with a different set of priorities. Meanwhile, the inner solar system became the focus of renewed attention. Mars, in particular, became a target of intense interest. The Mars Pathfinder mission in 1997, with its tiny Sojourner rover, captured the public imagination in a way that no outer planet mission had done since the Voyagers. The Mars exploration rovers, Spirit and Opportunity, which landed in 2004, became household names. Their years of exploration a triumph of robotic engineering. The Mars Science Laboratory, Curiosity, followed in 2012, and the Perseverance rover with its Ingenuity helicopter landed in 2021. These missions were expensive, but they were also politically popular. They offered the tantalizing possibility of finding evidence of past life, and they served as a stepping stone toward the ultimate goal of human exploration. Mars became the new frontier, and the outer planets, the realm of the Voyagers, were pushed to the margins. The Hubble Space Telescope, launched in 1990, also played a role in this shift. Hubble provided breathtaking images of distant galaxies, nebulae, and even planets within our own solar system. It allowed astronomers to study the universe with unprecedented clarity without having to send a spacecraft to every corner of the cosmos. Hubble was a powerful tool, but it was also a kind of substitute for the Voyagers. It could observe Jupiter's storms, Saturn's rings, and Uranus's atmosphere from Earth orbit, providing a continuous stream of data without the decades-long travel times and the immense cost of a deep space mission. The public could see the wonders of the universe without having to wait for a spacecraft to arrive. Hubble became the new face of NASA's scientific achievement, and the Voyagers, though still operating, faded from the headlines. The Cold War's end also reshaped priorities. The Soviet Union, once a fierce rival in space, collapsed in 1991. The space race was over. Without the competitive pressure of a rival superpower, the motivation for grand, symbolic missions like the Voyagers diminished. NASA's goals became more pragmatic, more focused on science for its own sake, and more attuned to the political demands of Congress. The agency's budget continued to shrink, and every major mission had to justify its cost against 100 other competing interests. A new Voyager, a mission to the outer planets with a price tag in the billions of dollars, would have faced an uphill battle for funding. It simply was not a priority in a world where the shuttle, the space station, and the Mars rovers were competing for the same limited resources. And yet, the Voyagers themselves continued to operate, a silent testament to what had been achieved. As NASA's attention turned inward, the two spacecraft kept hurtling outward, their nuclear batteries slowly decaying, their instruments still returning data. They became a kind of ghost in the machine, a relic of a bygone era, still doing their job long after the program that had created them had been disbanded. The engineers who had built them had retired, the scientists who had designed their experiments had passed on. But the spacecraft themselves remained, faithful and tireless. They were a reminder of what we had once been capable of, a challenge to the pragmatism that had come to define the space program. The shift in priorities was not a failure. It was a choice, a calculated decision to pursue different goals with the resources available. The Space Shuttle, the Hubble telescope, the Mars rovers, the International Space Station, these achievements are all worthy of celebration. They have advanced our understanding of the universe and our place within it. But they also represent a turning away from the grand ambition of the Voyagers. The idea of sending a probe to the edge of the solar system, of charting the unknown, of pushing the boundaries of what is possible, was replaced by a more cautious, more incremental approach. The myth of Voyager 3 is not just a story about a missing spacecraft. It is a story about the choices we make as a civilization, the priorities we set, and the dreams we decide to pursue. So the next time you look up at the night sky and wonder why we never built a third Voyager, remember the Earth below. Remember the budgets, the politics, the competing priorities. Remember that the space program is a human endeavour, subject to all the same constraints and contradictions as any other human enterprise. The Voyagers were a moment of extraordinary clarity, a time when the stars seemed within reach. But that moment passed, and the question of why we never sent a third is really a question about who we are and what we value. It is a question that has no easy answer, but it is a question worth asking. And yet, the story does not end with a closed door. Because, while we never built a spacecraft named Voyager 3, we have sent probes that carry the same spirit, the same ambition, the same hunger for the unknown. They just go by different names. The most obvious of these spiritual successors is New Horizons. Launched in 2006, New Horizons was designed to do for Pluto and the Kuiper Belt what Voyager did for the gas giants. It was fast, it was ambitious, and it was built to survive a journey of billions of miles. When New Horizons flew past Pluto in 2015, it revealed a world more complex and beautiful than anyone had imagined. Mountains of ice, plains of nitrogen, a thin atmosphere that glowed blue in the sunlight. It was a moment that echoed July of 1979, when Voyager 2 revealed the volcanoes of Io, the same sense of discovery, the same feeling of stepping into a place no human had ever seen. But New Horizons did not stop at Pluto. It pushed deeper into the Kuiper Belt, that vast ring of icy debris that marks the edge of the solar system. In 2019, it flew past a small object named Arakoth, the most distant world ever visited by a spacecraft. And New Horizons is still going. It is still sending back data, still pushing outward, still carrying the torch that Voyager lit more than 4 decades ago. It is, in every meaningful sense, a Voyager-class mission. It just wasn't called Voyager 3. Then there is Cassini. While Cassini was an orbiter, not a flyby, it explored the Saturn system with a depth and precision that Voyager could only dream of. For 13 years, Cassini circled the ringed planet, sending back images that rewrote our understanding of Saturn's moons. It discovered geysers on Enceladus, lakes of methane on Titan, and a complex dance of rings that still defies easy explanation. Cassini did not go interstellar, but it did something just as important. It showed us that the outer solar system is not a dead zone. It is a place of active geology, of potential life, of endless mystery, and Cassini was built on the foundation that Voyager laid. Without the flybies of the 1980s, Cassini would not have known where to look. But perhaps the most direct successor is the Voyager interstellar mission itself. The Voyagers are still out there. They are still sending back data from a place no other spacecraft has ever reached. And that data is shaping the next generation of interstellar probes. Scientists have already begun designing a mission called the Interstellar Probe, a spacecraft that would push even farther than Voyager, that would carry more advanced instruments, that would answer questions Voyager could not. But that mission has not been funded. It remains a dream on paper, a hope for the future. So why are these missions not called Voyager 3? The answer is simple. NASA does not name missions based on nostalgia. Each mission has its own goals, its own design, its own identity. New Horizons was not a Voyager because it was built for a different era, with different technology, different science objectives. It was a product of its time, just as Voyager was a product of its own. To call it Voyager 3 would be to erase its individuality, to pretend that the space program is a single continuous thread rather than a series of leaps and pauses and new beginnings. And yet, the public often misses this. They see the Voyagers as the gold standard, and they wonder why every subsequent mission does not measure up. But that is an unfair comparison. The Voyagers were a once-in-a-lifetime opportunity, enabled by a rare planetary alignment that will not happen again for more than a century. To expect every mission to replicate that achievement is to misunderstand the nature of exploration. Exploration is not about repeating the past. It is about finding new paths, new questions, new ways of seeing. Consider the Galileo mission to Jupiter. It arrived in 1995, 18 years after Voyager. It was not a flyby, but an orbiter, designed to study Jupiter and its moons over years rather than days. It discovered evidence of a subsurface ocean on Europa, a finding that has shaped planetary science ever since. But Galileo was not a Voyager. It was slower, more cautious, more focused. It was a product of a different era, when budgets were tighter and the public was less patient. And yet it achieved things that Voyager could not. Then there is the Juno mission, which arrived at Jupiter in 2016. Juno is studying the planet's atmosphere, its magnetic field, its deep interior. It is revealing the hidden structure of the largest planet in the solar system. But Juno is not a Voyager. It is a single-planet mission designed to answer specific questions rather than to explore multiple worlds. And that is okay. The space program is not a competition. It is a long, slow process of discovery, with each mission building on the ones before. Even the Mars rovers, from Sojourner to Perseverance, carry the Voyager spirit in their own way. They are robotic explorers, sent to places humans cannot go, designed to survive harsh environments and send back data for years. They are not as distant as Voyager, but they are just as ambitious. They are pushing the boundaries of what is possible, one step at a time. And then there are the missions that never were. The proposed Titan Mare Explorer, a boat that would sail the methane seas of Saturn's moon. The Europa Clipper, which will launch in the 2020s to study that icy moon's ocean. The Dragonfly mission, a nuclear-powered drone that will fly through the skies of Titan. All of these are spiritual successors to Voyager. Softies. They are bold, they are risky, and they are designed to reveal the unknown. So the question of Voyager 3 is not really about a missing spacecraft. It is about a missing mindset. It is about the public's longing for a time when space exploration felt limitless, when the sky was not the limit but the starting point, and that longing is real. It is valid, but it is also a misunderstanding of how science works. The Voyagers were not the end of the story. They were the beginning. And the missions that followed, from New Horizons to Cassini to the rovers on Mars, are the next chapters in that story. They are not called Voyager 3, but they are Voyagers nonetheless. Each of these missions answered questions that Voyager could only raise, and in doing so, they proved that the legacy of the Grand Tour was not a single moment in time, but a continuous thread of human curiosity. The torch was passed not through a name, but through a spirit of exploration that refuses to die, even when budgets shrink and priorities shift. And that spirit, as we are about to see, still collides with the cold, unyielding reality of what it truly takes to reach the stars. The cold, unyielding reality of interstellar exploration is something that the public rarely considers when it asks why we never built Voyager 3. The question itself assumes that building another Voyager is simply a matter of will, of funding, of desire. But the truth is far more sobering. To reach the stars, even the nearest ones, requires a level of engineering that pushes the absolute limits of what humanity can achieve, and it demands a patience that runs counter to every instinct of our modern, instant gratification world. Consider the power source. The Voyager spacecraft are powered by radioisotope thermoelectric generators, essentially nuclear batteries that convert the heat of decaying plutonium into electricity. When they launched in 1977, each generator produced about 470 watts of power. That is less than what a typical household light bulb consumes. Today, after decades of decay, those generators produce barely half that amount. By 2030, they will have to shut down the last of the scientific instruments. And that is for a spacecraft that was never designed to go interstellar in the first place. To build a probe that could travel meaningfully beyond the heliosphere, you would need a power source that could last for centuries, not decades. That technology does not exist yet in a form that is both reliable and light enough to launch. Then there is the problem of distance. Voyager 1 is now more than 15 billion miles from Earth, and it took over 45 years to get there. At its current speed of roughly 38,000 miles per hour, it would take about 75,000 years to reach the nearest star, Proxima Centauri. That is not an exaggeration. That is the cold math of interstellar travel with current propulsion technology. The public imagines a sleek starship zipping between solar systems, but the reality is a slow, silent drift through an emptiness so vast that it defies comprehension. Even if we built a probe today with the most advanced ion drives or nuclear propulsion systems under development, it would still take generations to reach even the closest star. The timeline is not measured in years or decades, but in centuries. And what would that probe find? The interstellar medium is not empty, but it is close to it. The density of particles in the space between stars is less than 1 atom per cubic centimetre. The magnetic fields are weak, the radiation levels are low, but they are constant. The probe would spend the vast majority of its journey, perhaps 99%, and the engineering challenges are equally daunting. A probe designed for interstellar travel must survive for decades without repair, enduring cosmic rays and extreme temperatures. The communication signal grows so faint that by the time it reaches the edge of the heliosphere, it requires the most sensitive antennas on Earth just to detect it. Beyond that, it becomes a ghost. The cost is another barrier. A single Voyager-class mission would cost over $1 billion today. An interstellar probe would cost several times that would not come for generations. The scientists who design it would never see its results. That is a difficult sell in a world where budgets are finite, and yet the idea has never died. NASA has studied concepts for an interstellar probe for decades. The technology exists. What does not exist? The technology to a mission that will not bear fruit for generations. The cold reality is not that we cannot do it. It is that we have not yet decided it is worth doing, knowing we will never see the results ourselves. The Voyager researchers have shown us what is possible, but also the price of that dream. The public expects a triumphant sequel. Yet the next great interstellar mission won't be a sequel, but a prequel to a story our great-grandchildren may finish. Why no Voyager 3? That question rests on a beautiful misunderstanding. The Voyagers were never the start of a pipeline. They were a once-in-a-lifetime shot, a cosmic alignment that has since closed. We didn't stop because we ran out of money. We stopped because that mission was never repeatable. And yet we have already sent Voyager 3, 4, and 5. They are New Horizons. They are Cassini. They just don't carry the name. The Voyagers still drift through interstellar space, carrying the golden records into darkness. Their voices grow fainter as batteries decay. Every day is a gift, a reminder that the greatest missions are measured in the quiet persistence of machines built by people who knew they'd never see the results. If this story moved you, hit like, subscribe, and share your thoughts. What should the next great interstellar mission be, and what would you put on its golden record? The Voyagers reflect our capacity for audacity and patience. They remind us that the distance between stars is measured in lifetimes. And yet we built them. We launched them. We listened. We haven't sent Voyager 3 because we've already sent something more important. A message that we were here, that we were curious, and that we dared to reach for stars we'd never touch. One day, long after we're gone, something may find them, and they will know we existed, that we wondered, and that we were not afraid to ask the question.